Okay, my name is Peter Gorm Larsen. I am also very grateful to be invited to be here to talk. I hope that you will enjoy my presentation. I will talk about the European approach to trying to use rigor in the way Dr. Fitzgerald was presenting before in order to use it in industrial applications. For those of you who do not know me, I've been here a couple of years ago. I'm currently a full professor at Aarhus University in Denmark. I also have a small company that I started up recently, but I've spent most of my career in industry. So I've always been interested in the exchange between academia and industry. This is the agenda I would like to talk to you about today. I would like to start with giving a short introduction to the notion of formal methods, to let you know what the kind of technology is that we are advocating here. Then I would like to continue with a survey of the trends that I'm seeing in industrial use of this kind of technology, both from our own survey and also a survey from the US. Then I'll make a jump and try to tell you a little bit about how the European Union have made its future strategy for research and development projects in collaboration between academia and industry. Professor Fitzgerald told you about a couple of such projects. I'll tell you about some other ones. Now, I'll give you an example of one of these, and one of these where we are trying to tackle what's called cyber-physical systems. And I'll try at the end to look ahead for future collaboration possibilities and a new project that will be started up next year. For each of these agenda slides, I'll show a small animation. The one you're seeing here first is what we call our Hello World animation for collaborative simulation, the kind of combination of a physical model and a model of a discrete event controller. But let's start with what formal methods are. First of all, formal methods refer to the techniques from logic and discrete mathematics that are used in the specification and design, precise modeling of computer systems and software. You may remember when you had mathematics in primary school, and some of you may think, oh, that was difficult or complicated, but actually it's not as difficult as many people think. The whole point here is that this is a technique to try to master complexity using abstraction. So I'll try to elaborate on these two notions. Essentially, the strategy is to reduce the argumentation thing to a calculation, which can be checked by mechanical means, and thereby replace manual efforts to a repeatable analysis. Here we see two pictures that illustrate aircrafts. They are very different. The one you see to the left over here is meant to analyze aerodynamics of the aircraft, whereas the one you see to the right over here is meant to be used for analyzing how it's like to be using flying in such an aircraft for a pilot. What is essential here is that these things do not need to look like what the real aircraft looked like. The one over here didn't need to have windows painted on it because that is not necessary for the analysis that they would like to conduct in order to find out the aerodynamics of an airplane. This one looks very far from what an aircraft looked like, but it's having the interior similar to what a pilot would normally see in order to make it specific for the purpose of the training of pilots. So when we try to model computer systems, we have in many engineering disciplines been doing this. And essentially, we make such models to gain confidence in the ideas we are having being appropriate. So we could put them into wind tunnels, like we did for testing the aerodynamics of the aircraft before. We could have stress models, for example. The point that is essential to the successful use of such models is the use of abstraction, to know what you do not need, what you can take away from the analysis. And then it's a matter of having rigor. That is precision. The things that are needed need to be incorporated appropriately. So let's look at what abstraction means. Essentially, what is important is to, first of all, know what is the purpose of the analysis we would like to carry out. Because the purpose determines what we can take out of the equation, what we do not need to think about. So, for example, when we wish to assess the aerodynamics of an aircraft in a wind tunnel, there are things we can say, if that's the purpose, then we don't need to look at what's inside the aircraft. If we have a cockpit mock-up, as we saw before, we wish to assess the human factors and to train pilots. If that's the purpose we have, we don't need to see the entire aircraft. We only need to see what the pilot is trying to do, and we want to assess how he's behaving. So the omission of detail that is not relevant is essentially what we call abstraction. But abstraction needs to be done with respect to a purpose. And this is the critical part. That's the part that's difficult. That's what we call engineering skill. And that part we can never replace. We always need the human being to help with that. So that's abstraction. I can recommend you to look at this paper if you're interested in learning more about abstraction by Jeff Kramer. If we try to take another example, this is a piece of text. I'll just read a bit of it. The flight finder system is to be used by travel agents and their customers. Details are entered, including point of departure, destination, preferred dates and time. The system will respond to a range of itineraries and fares, along with the relevant restrictions. That's a description of a system. Here's another description of the same system. The system records locations as nodes in a connected graph structure. Each node struct contains an array of pointers, etc. They're describing the same system, but the first one is trying to describe what we would like to see, whereas the second one is trying to show us how it's done. It's an implementation. The point is that the first one is more abstract than the second one. It's easier to comprehend. What we are doing with our formal models is something similar. We're trying to go as much as possible to the what, and then we try to take away things that are not essential, that can be abstracted away with respect to the purpose of the analysis we wish to conduct. If we go over to rigor, the important property of a model is that it needs to be suitable for analysis. If we just have a natural language text, the only kind of analysis we can make is we can read it. We can't make a tool understand it. So if we can only read it, it's up to the different opinions of the different engineers reading it. Whereas if we make a formal model that can be understood by a tool, by a computer, we can make machine support that supports it. In order to be able to make such machine support easy to comprehend, we need to make it rigorously defined. We need to make precise meaning of the language we are supporting. Thereby, there will be very little room for disagreement about what the analysis tools will say that the properties are for the particular model. If we look at technology transfer, which is one of the subjects of the event here, then formal methods in academia have had a tradition in Europe using abstract models. And there's been a focus on formal development. In Professor Fitzgerald's deploy project, you saw several steps of development. In the US, there have been a concentration on formal verification and automatic verification, typically at code level. So formal methods have been taught for a number of years at many European universities. It started off in the UK, where John Fitzgerald is from, and it has spread to other places. In Japan, I would say that both the technology usage and supply side is gaining strength. There are important projects that are coming in Japan. However, there are very different opinions by different stakeholders about the best way ahead for using this kind of technology. Here's a reference to a paper that's different than my opinion and different than Professor Fitzgerald's opinion. But I would like to try to give you what I think is the best way forward in a little bit later in my presentation. So I hope that this gave you a better understanding of what formal methods actually are and what they are about. What I would like to continue with is the trends that I can see in industrial use of this kind of technology, both in Europe and in the US. But before going there, I'll show you another little animation. The small arrow you see here at the top is indicating the user's input, kind of leaning forward or leaning backwards on this small Segway-like device, and the arrow at the bottom here indicating whether we would like the engine to go one way or the other way. So let's go on with the industrial usage. An example of successful application of this kind of technology can be found in the area of railways. B has been used all these different places on the Earth, particularly for metro systems and automatic protection systems for these. This is an involvement that has been going on for many, many years. It's not something that's easy to start up with. So I'll tell you more about that later. If we move to the US, we have a company there called Rockwell Collins, where you can see the time horizon for more than a decade, almost 2 decades, have evolved and used different formal techniques for different projects, and there is a connection between many of these. These are essentially kind of projects that can be carried out, but it requires a deep commitment from the organizations wishing to use them. So in 2009, Professor Fitzgerald and I and two more made a rather comprehensive survey of industrial projects using formal methods. At this point of time, we had a little bit more than 60 projects where all of them had filled in a questionnaire so we could compare them on a number of metrics. This was published in the ACM Computing Survey. In 2012, we made an extended version of this that is published as a chapter in this deploy book that Professor Fitzgerald was showing you earlier. We used the same format, but now we had almost 100 projects. We are actually planning on making a new update of this and to present that next year at the main formal methods conference. And now we have more than 100 projects. And we are hoping to gain more also from Japan. So in case you have any projects you would like to report about, please contact us and we'll give you the questionnaire. If we look at the 2009 findings we came up with, you can say it was a rather bright picture. There was an improved use of these kind of formal methods. There was an excellent success stories among these. And we had a dominating group of these projects that was using lightweight formal methods, meaning that they did not use the entire spectrum of things, just like Professor Fitzgerald was talking about earlier in the deploy project. But tools are critical. Increasing automation is present, but there's still a lack of usability. Many of these tools come from academic environments, and thus usability is not highly valued for publications of papers. In 2009, we lacked evidence with respect to what decisions were actually the reason why the companies were taking up this. We also lacked data on what happens when you use the same kind of technology in second project or third project or fourth project. There was also still a high barrier for psychology-wise in order to be able to start using this. So it was not something that people just did without having considered it. Training and education was vital, and that remains true. If we look at the 2012 status, we can say now we had 98 projects. They are distributed according to application domains like this. And we can say the main difference was that in the transport area and in the consumer electronics area, it has increased. If we look at it per application type, and one project can belong to more than one application type, there was a greater representation in real-time systems and in distributed applications. If we look at the technologies being used, it was broadly as it was in 2009. The market increases over time, in particular in the area of model checking and test automation. If we try to look at previous experience, then now we have substantial previous experience, which we did not have in 2009. So you can see half of the new projects actually had been using these kind of technologies before. And we can also see that the level of training required, obviously, if it's not first time you use it, it's much lower. If we look at the status in 2012, we can see with respect to time, how long time it takes to use it. Do you use more time on it? 20% said that. And do you use the same amount of time? Half of the people did that. And the people who said, well, we use less time, was 25%. When we go to cost, four times as many was saying that it actually is improving costs rather than losing money on using this formal methods technology. So a large portion, however, report that it has no effect or don't comment on it. If we look at the quality side, there's not much uncertainty. Virtually all of them was very positive. 88% reported that it was better than what they have used without formal methods. And there was not a single report stating that it was negative. So if we should try to conclude on this, it's probably that it's better and cheaper, but probably not faster. So I'd like to move to a different study. This study is made in the US, and it's done in a different way, because this is done using interviews. And they have interviewed 31 US stakeholders, and the stakeholders have looked at what are the main barriers for you to try to adopt this technology. In this survey, you will see that education and tools are the main barriers that needs attention. The main reasons why it's hard for them to adopt this kind of technology. Now, in the same survey, they also try to look at what would be the mitigation categories that could be used to help improve that situation. And again, education is way the biggest one, and tool integration, in particular tool integration towards the tools you already use, was the top scores. So the conclusions they try to draw from this study is that they're suggesting some strategies to address the educational barrier by means of making formal methods part of the undergraduate software engineering curriculum at more universities. This is a difficult thing to change because you need to have champions at these different universities who are interested in giving such courses. They also try to host courses in formal methods for working engineers. I believe something similar is happening here in Japan, and I think that's very positive. With respect to the tools barriers, the suggested strategies are to try to provide some governmental funding for integration of tools and to fund improvements to tool interfaces. They also try to suggest that they would like to see an encouragement of use of formal methods in new contracts. The majority of the stakeholders here come from the aerospace business. And in the aerospace business, you could, if you wanted to, as one of the requirements, state that you would like the use of formal techniques, which is also advocated for in certain certification documentations like DO 178C, and then try to create and disseminate evidence on the benefits. And I believe something similar is also happening here in Japan. I hope this gave you a little bit an idea of what industry in general is doing about these kinds of formal methods today. Now, I would like to change the focus of my presentation to give you a little insight into the European strategy for research and development projects in general, but in particular focus on the places where trustworthiness is important. Before moving there, I'll show you another small animation. This time is from the European Space Agency, where we built safety into this Mars robot, such that if it come up and is close to tilt, we would let it go back again, turn a little bit before we would try to move forward. So in this case, the European Space Agency had already made the model of the physical behavior of this device. We just built a better controller for this. So, but now I'd like to turn my attention to the European 2020 Horizon 2020 program, and with focus on trustworthiness. So the European Union have a program that is set up entirely to 70 billion euros. That's a lot of money. The core part of this is essentially trying to respond to the economic crisis all over, and then try to invest in future jobs and growth. The idea is that they would like to try to address people's concern about the societal challenges, but also trying to strengthen the European position in research, innovation, and technology. The Horizon 2020 program is divided into 3 pillars. The one at the top is excellent science. The one to the left is industrial leadership. And the one to the right here are the societal challenges. Now, I would like to go further into the industrial leadership place, because that's the place where there's most emphasis on the trustworthiness. Now, the industrial leadership is having motivation by means of being a strategic investment in key technologies, for example, advanced manufacturing and microelectronics, that are going to be the enabling factors to key innovations in the future. Europe needs to attract more private investment in the research and innovation, and they would like to see more of the small companies, the small and medium-sized companies, create growth. And this program is meant also to help them. It's divided into a number of areas. In the ICT area, and I've only taken the ICT area, where we have components and systems, we have next generation computing, we have future internet, etc. And I'll take a few of those and try to illustrate to you the amount of budgets that are there and the opportunities that are there. So if we take component and systems as an example, there's an overall budget for 142 million euros. It's going to cover different kind of cyber-physical systems and system integration things. Also, the electronic components at a more nano-level scale, but they're being grouped into related topics such as these, and I'll focus specifically on the one called Smart Cyber Physical System in a new project that's just been granted and will start in January when I come a little bit further in my talk. So the areas here are described in text, and there's lots of text. I'll not present all of that here. To give you an example of another area that is strategically important to Europe, you see robotics. That's definitely an area where Japan has a research strength. And they are making them into what they call public-private partnerships, PPP, in order to both let the public and the private companies do investments together with the Commission, who are then giving additional support. Another area that is having attention and also having focus on trustworthiness is the way manufacturing is done. In Europe, we have lost lots of jobs in the sector where things are being manufactured. So there's an incentive to try to say we need to improve, we need to use more innovation to do these things better. And the trustworthiness of these things are essential. And this is one of the places where cyber-physical systems also are dominant in their place. So I hope this gave you a little insight to what it is Europe is doing when it's funding projects like Deploy that Professor Fitzgerald was talking about before. I would like now to turn my attention into another of those projects, one that is used for cyber-physical systems. And before going there, I'd like to show another animation, this time of an excavator. And all the animations I have shown you here are actually used coming out as byproducts of collaborative simulations that you're going to see how they can be made now. This project I'll talk about now is called DESTEX. This was also a project where both Professor Fitzgerald and I took part in it. And the idea is to have a model of a discrete world, typically a controller in a computer, and a model of the physical plant and its environment that is interacting with the controller that we would like to have. The discrete side here is modeled using something called VDM real-time. That's a dialect of VDM that enables the modeling of distribution and real-time aspects. And the tool being used here is an open source tool called Overture. The physics is described using something called bond graphs in a tool called Twentesim. Twentesim is a small spin-out of the Twente University. What is important for control systems like these is that typically 80 or 90% of the software is actually not the low-level control, the PID control. It's the supervisory control. And that needs to take different faults into account. So what we are able to do here is we can inject faults different places in order to try to model our controller such that it can be tolerant against such faults. So in this project, we have developed methods, guidelines, and patterns that are applicable to people. We have also developed tool support on top of an open platform, and we have had industrial case studies, both a personal transporter, the Segway-like thing you have already seen, a mail processing device that you'll see in a moment, and then a dredging excavator that you have just seen a simulation of as well. What is important is that the animations there are mainly used as a communication medium to people who are not technical experts. All of this is being described also in books. A new book came out this year. We'll see how it fits together later. There's currently an initiative trying to find a Japanese Japanese publisher for the Japanese version of the book. And there's also other documentation that we can circulate in case you're interested in looking at it when we have the next break. Now I'll start by showing you a small video. Can I connect myself to an audio system? Okay, let's just try.
In a folder inserter, two paths come together, the envelope path and the paper path. The envelope has to be separated and transported to the inserting area. Of course, the flap has to be open too. Then the envelope waits for the set to arrive. The paper path starts with the feeding process. One sheet has to be separated from the rest and transported. Then the second, and maybe a third, or even more, have to join the first one. When the set is complete, it is folded. After folding, it is transported to the inserting area.
So essentially, this is like a printer where you feed paper in, except that this have already printed letters. Imagine you have to send out 1,000 letters by physical mail. This machine is able to take all the letters and fold them and insert them into envelopes. However, the critical part about that is that when you are folding these pieces of paper, if they're not fully aligned, so if the line is a little bit skewed, what happens is they don't fit inside the envelopes. So what the company here did was to make a model of this folding process, and the key results here was that they were able to spot a mechanical design error even before they had made the first prototype. They also had a use of the model they made in the sense that they used it whenever, even when they had the prototype finished and they had it available, there was enough fight for who can be able to use that prototype. Typically, you both have mechanical engineers who would like to test different aspects, and you have software engineers who would like to test their control algorithm on it. So here they saved one physical prototype in their development. Here you'll be able to see such a prototype in operation. And here's the actual paper being processed forward. And you can imagine that testing this in a physical world can be a tiresome thing to do. So if we move to the self-balancing scooter, which was the second case study used in this project, you're already seeing the animation coming out of the collaborative simulation, which can be performed using this technology. What you see here on the right-hand side is actually, this is the first prototype being made based on the designs conducted. This one had one CPU, a central computer, did not have real steering. The second one, you're going to see it now, is trying to do distributed control and then having a connection with a bus in between these two. This gives other complications. The whole point is that the technology here enables you to do a trade-off analysis. You can try out different things in this virtual environment before you commit to prototypes such as these ones. Here, they discovered several design conflicts by means of using this collaborative simulation. And essentially, the system behavior included the fault handling. Fault handling is very important for something like this because you can have malicious users who are not using the system appropriately. And the test and integration phase was very short because it was virtually right first time. Here you see a dredging excavator. These devices are also being produced here in Japan, and they are in the Netherlands and Belgium being used in the canals to clean the bottom. And what is essential is that the operator, you see how concentrated he looks over there, has difficulty in seeing what he's actually doing because he's digging underwater, and he needs to have experience in how hard he's pushing the device. In order to test this, we produced a 1 to 12 scale prototype looking like this over here, and it has different kinds of devices. You have 3 different dimensions you can move, and then there were linear actuators rather than the hydraulic things used at the real system up here. What is happening is that when you try to operate something like this, if you are unexperienced, you may destroy the material. So the end stops of these things can actually break. Here we see both a animation coming out of it, and here you'll see a use of the prototype. Just turn down the volume. What was used here essentially was also this design space exploration to determine where would we try to put something to prevent the operator to get all the way to the place where it would crack. And you can't stop it immediately, so you have to stop it gradually. And that was what design space exploration was used for, to determine the best protection parameters to ensure this. What you see here is another mode, assisted mode, where the placement of the place you are digging is constant. So we can actually avoid the kind of complex behaviors that an operator needs to make if he wants to dig the same place. He needs to use multiple of the joysticks at the same time, which is difficult. Therefore, this assisted mode was helping to do that. And then it was validated using this scale-up model. So there's also supporting material for this. The book to the left is a book on VDM++. It's also available in a Japanese version. So I didn't bring a copy of that. But the book here to the right is a book describing how one can model physical systems using essentially differential equations. And the book in the middle is the book from this project. The book that describes how you can actually go and use this kind of technology, and where a Japanese publisher is being negotiated with at the moment. So I'd like to end my presentation by trying to look ahead for our future ideas and potentially collaboration possibilities with any of you who are interested. The animation I'd like to use this time is actually for a small robot that is doing autonomous feeding of mink, this furred animal that are inside the small caves here. And the feeding thing here is done by one of my PhD students who currently is on leave from his PhD studies, working at the company developing this in order to get it all operational. So we have a follow-up project to the DESTEX project I told you about before. It's called Into CPS. CPS stands for Cyber Physical Systems. It's a new €8 million project under this Horizon 2020 I told about earlier in the Smart Cyber Physical Systems objective, where DESTEX was concentrating entirely at the modeling level. This project is going all the way from requirements using SysML down via heterogeneous system models that can be simulated at the modeling level using an interface called functional mock-up interface, and then also having hardware in the loop and software in the loop simulation capabilities together with code which is being generated or actual pieces of equipment, actual hardware. We have still the design-based exploration capability, but also a test automation capability that we intend to build here. All while we have full, strong traceability and configuration management, so we have a full notion of all the experiments we have conducted while we have carried out our projects, and know what kinds of artifacts that constitute the evidence we would like to use for a justified argumentation of the system we are conducting. Now, here is a different figure trying to show the same thing, where we come from requirements down to architectural models that will generate contracts in between the cyber elements and the physical elements and the environment model that we can have. And these can together be co-simulated and produce the kind of animations you have already seen. A number of other plugins will also be included, and then you can have these hardware in the loop and software in the loop simulations together with real code and real plants. In order to do a gradual introduction, so gradual integration of things rather than doing a big bang integration, which typically is happening today in industry. The consortium for the project here consists of 11 partners. I am the coordinator of it. Professor Fitzgerald is responsible for one of the work packages, and then there are a number of other partners here as well. We have 4 large case studies, similar to the case studies you have heard about in Deploy and also in the DESTEX project. We have one in railways. Actually, that is the company that is being using B all over the world, called Clearsea from France. We have a company in the agriculture sector who will try to use it for the kind of implements you put after a tractor. We have an automotive case with a company from Germany who is trying to do this kind of thing for many of the German manufacturers. And we have United Technologies using it for building automation, in particular the air conditioning systems that they also deliver in an avionics sector. So this is a new large project. Like we had in the DESTEX project, we have what we call an industrial follower group. In the industrial follower group, when we wrote the proposal for this, we had these partners saying to us already, this is interesting, we would like to follow what you're doing while you're doing it. And we have one from Japan. I'm hoping that more of you find something like this interesting. And if so, you please contact me and let me know, because it's free of charge. You would just be able to get access to the technology before it's being released to other people and receive newsletters, etc. So the challenges that are necessary to make the tools I've just described is that the foundations, the methodology, the practice and experience needs to fit together, just like Professor Fitzgerald was explaining earlier. The deployment to date, so you've seen some of the things from the DESTEX project, have been quite encouraging. The semantic basis have been made for the DESTEX thing, but we are going to use other formalisms as well and other notations and tools as well. The model interchange will encourage the methodologies to develop further in this kind of interactive way where it's not going technology transfer in one direction. We learn and they learn. So it's pragmatics, from a pragmatics perspective, what is important is we improve the performance of the simulations we are able to conduct. So what also is important is to encourage what I call cyber-physical thinking. Thinking such that you can actually do trade-off between what is done in by mechanical means and what is done by software. So you can actually change things dynamically before you are finished with your design. So at the very last slides here, I'd like to turn my attention to the thing that's being asked in the panel session we're going to have afterwards, and that's about how we do technology transfer. My first advice here is that you should try to create an evolution rather than a revolution. So unless you are very strong and have skills in your organization that knows about former methods quite well, it would be best to try to make small steps. Try to take a small project and you can try to say, we'll use it for this small part. Possibly start in parallel with a traditional method, but of course it's more costly. But that is what Professor Fitzgerald and I did with British Aerospace. If you try to make a large revolutionary change, it's much more likely that you're going to risk too much. So if you wanted to do what we see Clearsea and Rockwell Collins have done, you needed to have had a long and strong background in being able to do so. So moving to this approach, taking for B in railways and Rockwell Collins, that requires a long-term commitment. And my recommendation is to kind of take small success stories along the way. So you can ask yourself if you think you can use former methods. Yes, I'm sure you can. But what's important is you need to invest in education. If you don't know about it already, you need to learn. And you need to start using it places where you know you have problems. If you have something that works well, there's no point in trying to change to a new technology. But in particular, if you're involved in the development of critical systems or involved with complex data or functionality, then I think it is important to try to go this route. But don't consider former methods as some kind of wonder medicine that is going to help you with all possible problems. It's important that it's being used first and foremost by a few people that are the key people to design the future solutions you wish to have. Get advice from an expert. There are several of them here in the room today. The point is that I have been training people both in industry and in academia for more than 20 years. And it may be me not being poor at teaching, but I still feel that the ability to do the right abstractions, my skill set is just still a factor of between 10 and 100 better than all the students I have had, or at least most of the students I have had. So what is important is that you have an expert who can help you, and you have many opportunities to find them in this room. So the things I would like you to remember from this talk is that former methods have been used in many different kind of industrial contexts. They've also been used outside critical applications. It's not just for critical things. The European Union have made a program, Horizon 2020, which is giving opportunities in Europe for close collaboration between industry and academia. Whether Japan wish to do a similar kind of initiative, that's not me to decide, but I think that this works quite well. We've shown you about some projects that are useful for trying to increase trustworthiness You've seen Professor Fitzgerald talk about a couple before, and I've talked about one existing and one new one. And the general attitude I have is that I think that formal methods should be used whenever it's needed. You shouldn't always use them. You should use them where you have something that's difficult, something you need, you can get help with by using the abstractions. And remember that a fool with a tool is still a fool. Therefore, you need teaching. Training and tool support is essential. So contact Professor Fitzgerald or me if you wish to discuss your possibilities and what you could do, or contact IPA SEC about the possibilities as well. So with those words, I'd like to thank for your attention and show the robot you saw earlier as a co-simulation. Here's the real thing being demonstrated with the same parameters for the control as derived in the co-simulation earlier.